So, as we are looking at the special case for an electric field, because if we know the charge arrangement or what kind of charge or what shape the charge creating the field has, we can get very specific and not have to use the general, always true definition that we just used in the previous video. We can now look at the special case where the electric field is caused by a point charge or a sphere of charge. And in this situation, we're going to use a combination of the definition of the electric field, which we just went over, and Coulomb's law that the electric force is equal to K times the magnitude of Q1 times the magnitude of Q2 divided by the distance between those point charges squared. And Q1 is going to be capital Q, the charge creating the field, and Q2 is going to be our test charge, Q naught. When we enter this, we can see that we have Coulomb's law divided by Q naught is equal to Coulomb's law times 1 over Q naught, which simplifies to the ever lovely the electric field for a point charge is K times the magnitude of the charge creating the field divided by the distance from the center of that charge squared. Now, this only works if we're talking about a point charge or a sphere of charge, and the direction is always going to be given by our definition of the direction, which is that the electric field is in the same direction as the electric force experienced by a small test charge at that location. So, let's do a quick example. We have a sphere of charge that is a positive 18 millicoulombs that creates an electric field. There's a point in space, P, and it's located 15 millimeters away from the charge. So the distance from the center of the positive charge to P is our 15 millimeters. We don't want that in millimeters. We always want this in meters. So that distance is 0.015 meters. We've got a positive charge. So if we look at our positive charge creating the field, right, and the field would be everywhere away from this positive charge, and our point P is to the right of it, meaning at point P, it will experience a direction to the right. And then when we go to actually calculate this, what we will end up doing is simply grabbing our equation for an electric field due to a point charge, which would be E is K magnitude of Q divided by R squared, which would be 8.99 times 10 to the ninth multiplied by the absolute value of 18 times 10 to the negative third, because milli is negative 3. And then dividing by our 0.015 quantity squared. And when we punch this in through our calculator, we're going to notice something, that while typically we tend to get relatively small forces, electric fields can be absolutely ginormous. So it's gigantic, it's huge, it's ridiculous. And to our three significant in this case it's only 2, so the 2 sig figs, it would be 7.2 times 10 to the 11th newtons per coulomb.